Hello and welcome to the Open Systems Media eCast titled Managing SWaP in ISR Systems. My name is John McHale, Group Editorial Director with Military Embedded Systems Magazine and moderator for today's event. Our speakers today are Brian Musica, Sales Manager for Defense and Aerospace at Advanced Cooling Technologies, Aaron Frank, Senior Product Manager for Intel Single-Board Computers at Curtiss-Wright Defense Solutions, Michael Stern, Global Product Manager for Mil-Aero Products at GE Intelligent Platforms, and Greg Powers, Market Development Manager for Aerospace, Defense, and Marine at TE Connectivity. Now, before we get started, I have some short housekeeping announcements. The eCast will consume about 35 to 40 minutes, leaving the remaining time for the question and answer session. Before we get going, I want to point out three important buttons on your screen as well. First, please take note of the Enlarge Slides button. By clicking on this button, you'll be able to view the slides in full screen mode. The second important button is the Forward to a Friend button, which enables you to send an email request for this event. The third button on your console window allows you to enter questions in real time. We will do our best to address these questions during the closing Q&A session. If you have a question intended for a specific speaker, please note so at the beginning of your question. Otherwise, I will hand out the questions equally to our speakers. If you have a question pertaining to the eCast operation of itself, one of our technicians will respond back to you during the eCast. Please note that as much as we'd like to, we may not get to all of your questions today. In that case, someone may get back to you after the eCast with more information. The eCast will be archived online and will be available for 1 year. There will also be an MP3 version of the event. And now I'm pleased to turn over to our first speaker, Brian Musica. Brian?
Thank you, John, and thanks everyone for joining us today. As he mentioned, I'm the Sales Manager of Advanced Cooling Technologies, and I'll be kicking off our discussion today to talk about how to improve your size, weight, and power, your SWaP considerations for your thermal management solution. So most applications require some form of conduction. It's rare that there's enough available space for a heat sink in close proximity to all of your critical heat-generating components, and therefore heat spreading is one of the most important considerations in your system. In most embedded computing, optical devices, and electronic cooling systems, it's the primary thermal management concern. Heat spreading, looking at some of the performance dictators, is dependent on the thermal conductivity of your heat spreader, the cross-sectional area, as well as the length that you need to move the heat. So to enhance SWaP, thermal performance should be maximized and your size and weight should be minimized. What we're doing in this slide is investigating two-phase heat transfer solutions compared to bulk material conduction solutions. If you look at the graph in the top right, you can see that the two-phase heat transfer devices, such as heat pipes, high K plates, and vapor chambers, have much higher thermal conductivities than the bulk metal solutions, such as copper and aluminum. For instance, a heat pipe can move heat with an equivalent thermal conductivity of 10,000 watts per meter K, compared to aluminum, which is 167, or copper, which is 380 watts per meter K. The range we show for a heat pipe, 10,000 to 200,000, is mostly a function of its length, because a heat pipe, the temperature difference across the length is not largely reliant on the overall length. So the longer the heat pipe, the longer that effective conductivity. For most electronics cooling applications, heat pipes are around 6 to 10 inches in length and are somewhere near the lower end, the 10,000 watts per meter K value in that scale. Heat pipes do move heat in a single direction, so it's a moving from point type spot cooling type application. If you need multi-directional heat spreading, you may look at a high K plate or vapor chambers. These type solutions have the highest thermal performance, left in the chart. For instance, high K plates have over 500 watts per meter K and as high as 1,200 watts per meter K in bulk thermal conductivity. Also shown in the table to the right is considerations for weight. This table normalizes the density to that of aluminum. So if you look at a high K plate, this has kind of the highest pound-for-pound multi-directional thermal spreading capability. So the density here is very comparable to aluminum, but the K value is much higher. A high K plate has embedded heat pipes, which are held in place with solder, which is only slightly more dense than the aluminum base, so the density range is pretty much a function of how many heat pipes are used in the system. So now that I kind of gave you the overview of the SWaP considerations, now we'll dive a little bit more on how these type of solutions work. So in this slide, we're talking about heat pipes and how they passively transfer heat. So in a heat pipe, there are no moving parts and there's no input power required. They are basically an evacuated tube, which is comprised of an internal wick structure and a working fluid. Overall, heat pipes can move anywhere from tens to hundreds of watts, and that is largely dependent on the geometry and gravitational orientation as you're aligned in your system. The operation of a heat pipe is completely passive, which is one of their main benefits. Looking at the figure to the right, the heat source, at the heat source location, the working fluid vaporizes and forms an internal pressure gradient. So the vapor inside moves to the cooler region. At the cooler region, the fluid gives up its latent heat and condenses back to a liquid. This liquid is then passively pumped back to the heat source end by capillary force provided by the internal wick structure. As I touched on a little bit before, high K plates are heat pipes embedded into aluminum or another base material. Here we're showing a cross-section in the top right, which points out kind of how a heat pipe is implemented into the plate. Basically what we do is press heat pipes into the plate and solder over top, and then we do a secondary machining, which allows the heat pipes to be extremely close to the surface or to your component to capture and transfer that heat into the heat pipe, and then use the two-phase heat transfer to spread the heat out very efficiently. This process also allows for a very smooth mounting surface to mount your electronics and other critical components, so you don't have to worry about different surface profiles. And overall, you can end up with a very thin workable frame, which is as thin as 72 thousandths, and it can provide thermal conductivities ranging from 500 to 1,200 watts per meter K, as I mentioned previously. Just wanted to touch on those results. Those are real-world test data results where we measure our delta T's with an actual test application delivered to a customer, and then we go back into our models and put a bulk thermal conductivity in and basically increase that bulk thermal conductivity until we actually match the hotspots in our test fixture. And so it gives you a real-world value that you can go into your models and put somewhere in that range and feel confident that we can meet that performance. These plates are also ruggedized for harsh environmental conditions. Most platings that you can add to an aluminum plate can also be applied to a high K plate. So it's routine that high K plates pass thermal cycling, shock, vibration, and various other environmental concerns. A lot of times companies will ask us about the CTE mismatch between the heat pipe, the solder, and the base material. But we've demonstrated thermal cycling for these plates, hundreds of thermal cycles, and basically what happens is the CTE of the base plate dictates the overall thermal expansion coefficient, and the heat pipe and the solder kind of just go along for the ride. So it has been demonstrated thermal cycling in a lot of numerous thermal cycles. So one of the areas where we utilize the high K plates for enhanced heat transfer is at the board level of electronic systems. By using a high K card frame, for instance, you can get several SWaP benefits that are not achievable with a simple metal spreader. You, first of all, get the higher heat transfer rate associated with the high K plate, but you also get the design of the heat pipes to route them along your edge and isothermalize the card edge. This allows you to lower your thermal resistance at this interface, so as you transfer heat into your chassis or into your next level assembly, you don't have a large heat flux at that interface, which could drive your temperature difference. The heat pipes also do most of the thermal work, so you can thin out your frames as much as possible or add weight reduction pockets to further your weight enhancements. For air-cooled systems, high K plates can play a large role in reducing your conduction gradients under the fin stack. This can create higher fin efficiencies and oftentimes lower the required fin volume. So if you look at the bottom right figure, you can imagine a heat pipe directly under those fin stacks, and if there was a hot spot in the middle, you could spread that out evenly across the entire geometry and dissipate a lot more heat with a lower temperature gradient. So now what we're going to do is look at a application that is kind of prevalent in the embedded computing world. And in this case, the customer had heat loads that increased dramatically from one design to the next, and they didn't have the schedule to do full redesigns of their system. So instead, they looked at a quick retrofit type design, and basically what we're showing to the right there is the boundary conditions of the system. It was cooled along the base with a liquid cold plate, and basically what they needed to do is get the heat out of those card guides and bring it down to that base as efficiently as possible. And the solution that they ended up going with was going with a high K bolt-on plate. So we designed the heat pipes to move heat directly from those card slots to the base, basically just straight heat pipes down. And the plate was just bolted on externally to the chassis, allowed for no redesigns to their legacy parts, and was very efficient at moving the heat down to that base. So in this final slide, we're showing the results of that system. So if you remember the boundary conditions, basically what we need to do is move the heat to the base, and the heat pipes were embedded to efficiently do that. If you look on the left-hand side of the picture, the aluminum spreader, we basically mocked up a similar-sized aluminum plate, bolted it on, and ran some thermal models and determined that they would have around an 82-degree temperature at their hotspot electronics. When we did a similar analysis with the high K plate, we were getting down to about 32 degrees. So you can see that there's about a 61% reduction in overall temperature gradient, and it gave them a lot of flexibility in their design to add more heat into their system, add more capabilities, or they could do various other weight reductions in their system to improve overall SWaP. And that wraps it up for the thermal portion. I wanted to hopefully give you guys some valuable tools for the thermal and mechanical engineers out there that deal with these heat transfer problems. Hopefully you got some ideas on how to improve thermal performance as well as reduce size and weight of your system. And with that, I'll pass it back to John. Thank you.
Thank you, Brian. Excellent presentation. I'd just like to remind the audience, send your questions in if you have any for Brian. Shoot them through now. We will get to them after our fourth speaker during the Q&A session. And now for our next speaker, Aaron Frank, Curtis Wright. Aaron?
Thank you, John. Good afternoon, everybody. This is Aaron Frank with Curtis Wright. I'd like to share with you today what we're seeing in the ever-present trend to reduce size, weight, and power, specifically in the area of processing and specifically ISR processing. And I'd like to tie all of these trends into the growing capabilities that we're seeing with Intel processors. As we are all aware, what we've seen in the traditional ISR application space has been complex, very specialty-built systems, which were typically very large, very high-powered, very hot systems. Initially, these systems were all ground-based, and over time, they moved into the air and into a variety of different platforms. But today, these same systems need to be deployed on smaller and smaller platforms, which severely hinders our ability to meet the size, weight, and power targets with the traditional ISR architecture. And as you can see in the pictures of this slide, some deployment examples where the most SWaP critical ones are shown in the right side, where we have small UAVs, some even handheld, which can be used for various levels of our ISR applications. The other trend that we're seeing, which I'm sure is not a surprise to most listeners, is that the technical requirements of ISR systems are not diminishing as the systems become smaller. In fact, they continue to become more and more complex. With imaging systems, they seem to have a much higher resolutions these days and require a higher level of processing than we have in the past, with the same or higher throughputs to ingest data, analyze data, store, and relay information. And the same is true with other ISR-type applications. And of course, we're all aware of the ever-shrinking defense budgets and things like sequestration. So we do need to find ways to cost-effectively reuse developed intellectual property and to leverage these existing systems and architectures. There's also a trend towards rapid development and deployment and of fielding common technology into many different platforms, be that multiple airborne systems or a mix of airborne and ground-based systems. And of course, SWaP is the key for all of these to meet the demands. So I'd like to take a look briefly at what we call yesterday's systems, which are really multi-processor or many processor systems. These are systems that contain many different processing boards, each with one or more single-core processors. In the past, the workhorse of many of these systems were power architecture processors with AltiVec processor engines, effective processing engines. There's also other custom DSP-based and FPGA-based systems. And today, we're seeing a move towards using a common computing platform to do a lot of these same functions. In these many processor systems, we also see a variety of different fabrics used to tie them together, including Ethernet, Serial Rapid I/O, VME Bus, PCI, Star Fabric, and others. On the software side, a variety of different software environments were used, including VxWorks and Linux operating systems, and a whole range of different APIs to use in terms of application software development, and also using of custom libraries tailored to the specific hardware. And of course, the more boards and hardware that are required to get the job done, the more power is required and the more heat generated and more weight and so on. So let's flash forward to today, and we can look at the latest generation of processors from most vendors, most notably Intel, Freescale, and AMD. And these vendors have integrated multiple processing cores into a single piece of silicon. Although the sweet spot seems to be 2-core and 4-core processors, which are driven by today's desktop and laptop computing world, there's also processors with more cores, such as the 8-core hyperthreading Xeon processors, or Freescale, which has a 12-core dual-thread or 24 virtual core processor that can be used on a single piece of silicon. What we're also seeing is that the core-to-core interconnect fabric is typically a high-speed bus with multiple levels of processor cache to ensure that the processors are not starved when they share common memory interfaces. And of course, with multiple memory channels, the processor can take massive amounts of data and feed the processing cores. The other thing we're seeing is that the processing cores have specialized accelerators that can be used for math-intensive processes. So for example, the Power Architecture series has brought back the AltiVec processing engines, whereas the Intel Core i7 family has vector processing engines known as AVX or AVX2 processors, instructions. And they also have onboard graphics accelerators, which can also be used as general-purpose GPU processors, offering in excess of 350 gigaflops of floating-point performance and upwards of 20 or more GPU processing engines, again, in a single piece of silicon. And common to all today's processors is PCI Express for connectivity to the outside world. I'd like to talk for just a moment about the Intel processor technology cadence and how it relates to managing risk in the adoption of new technologies. Intel, as everybody knows, is the de facto standard for the desktop world and has for many years adopted what they call the tick-tock model. What that means in the semiconductor world is that there are two primary high-risk activities. One is the changing of process technologies, which is a high-risk activity as new processes bring in new tools, new models, and new unknown challenges. On the other hand, changing the internal architecture of a chip is also highly risky, as the new design techniques and algorithms are developed and validated. So Intel's tick-tock cadence really permits only one of these things to change. They either change the process or they change the architecture, but not both. And that has a huge benefit in terms of managing risk from generation to generation as technology advances. So here's an example of a 3U processing board built around the latest Intel Core i7 processor. With 4 cores and 8 threads running at 2.4 gigahertz, the raw computing power of this processor exceeds 173,000 TriStone MIPS. Compare this to a common processor of yesteryear, the 7447 Power PC processor, which gives approximately 3,000 MIPS, and it's a huge, huge jump in performance. Now add to this, the processor has built-in AVX2 vector processing engines, which provide roughly 300 gigaflops, and then the graphics processing GPU, which adds another 350 gigaflops. And we can see that the power in just this single board and single processor is the equivalent of many, many of yesterday's 6U boards. And as a comparison, the discrete GPU functionality of standalone GPUs tends to be higher, but not integrated as tightly as a single chip solution such as the Intel. Lastly, to get data in and out of the processing engine, PCI Express connections are typically used to communicate with other boards in the system. And today's rates, that gives you up to 8 or 16 gigabytes per second of connectivity of a fabric that's built into the silicon. Again, saving size, weight, and power for extra chips that wouldn't necessarily be built onto a 3U board. So putting this all together, let's look at a system example where we have 3 processing boards. And this is just one example of a small ISR processing system. In this particular system, we've put together 3 single-board computers with Intel processors used to acquire and digitize sensor input, with 2 of the boards, and a 3rd board being used to further process the data for analysis, display, and storage. This 3-board combination has close to 2 teraflops of floating point performance, and because they're standard 3U VPX form factors, the entire signal acquisition and processing core here can occupy an area of just 60 cubic inches. The total power of such a system is under 200 watts, which is quite manageable in the 3U form factor. So when we look at the larger picture of a deployable system, I think we can all agree that the thermal design challenges with 3U boards tend to be much simpler than 3U boards due to the proximity of circuitry to each of the 2 side cooling walls of a chassis. And by using multiple single-board computers, each with its own multi-core processor, the heat is better managed across multiple modules in the chassis. And then using high-performance fabrics that are typically built into the chip, such as PCI Express, and optimized software middleware such as shared memory drivers, OFED, and vSIPL libraries for optimized vector processing in a standard software application perspective, we can achieve both the performance and also the ease of development and portability that we need to rapidly develop and deploy today's ISR applications. And of course, the result of all of this is a lower overall development and deployment cost and a huge reduction in the size, weight, and the power compared to similar 6U systems. Thank you very much, and with that, I'll turn it back to John.
Thank you very much, Aaron. Excellent presentation. Just another gentle reminder, get your questions in. We'll get to them after our last speaker. And our 3rd speaker is coming up next, and his name is Michael Stern, and he's with GE Intelligent Platforms. Michael?
Thanks, John, and thank you, Aaron and Brian, for starting out so well. I'll pick up on a couple of points made in some of the previous presentations and lead you through my little slide deck, which is probably too long and will force me to speak fairly quickly, but here we go. So I'm a product manager within GE, and I work with a team of people who put together high-performance embedded computing solutions for ISR applications. These are some of the topics I'll try to cover in this short presentation, and as John said, feel free to put your questions in so we can get to them at the end. So I'll try to just outline some of the typical platforms that we try to address with our open architecture platforms. We sell both hardware and software that's optimized for these types of applications. And I'm going to be stressing a little bit more on the software side today, just to talk about, for example, in the first presentation we heard about how to get the heat out, but another way to think about it is how to use your resources really efficiently so that you're not generating as much heat for every cycle of the CPU that you're using. So these are some of the bullets I'll try to cover. A little bit about the value proposition on high-performance computing that you see in many high-performance applications like data center and scientific computing, typically based on Linux clusters. A little bit about how we tune for size, weight, and power and cost-sensitive applications in defense. And then some examples on a product that we have, which is a software environment that allows you to tune for these types of platforms. So what I have here is I've put together a little diagram. It's fairly generic. but just wanted to use it to illustrate some points about a typical sensor processing application, which might be deployed on an airborne platform or a ground mobile platform, or indeed some kind of naval platform. And what I'm trying to show here is that for back-end processing, which is the little dotted square on the right, we have an opportunity to use an open system architecture. And as Aaron said in his previous presentation, the Intel chipsets that are coming to market today, both from the laptop end of the spectrum all the way to the Xeon server class, are extremely high performance per watt processors with extremely good signal processing capability. The AVX engine within the Core i7 is outperforms some of the previous PowerPC AltiVec platforms that have been in wide use for many years. And indeed, we have applications where customers have taken what used to be 3 quad PowerPC boards and replaced it with a single dual node 6U card and had headroom to spare for example, radar type applications. But the really big bang for the buck is on this next slide, and that is that by using applications that are developed on high-performance Linux clusters or servers or desktop machines, we can leverage a really big community of people who are very clever and who understand how to do data processing very efficiently. So what I'm alluding to here is that in addition to the ability to do DSP and sensor processing to extract targets from ISR chain, be it images or radar or signals intelligence, there's an opportunity to integrate very advanced analytics on the back of that, and to bring that in within a Linux environment allows you to take applications that have been developed by a diverse community of intelligence analysts and also your embedded system developers, which are the people developing the DSP type applications, and to leverage that into a deployable system in various form factors. So here again, we're typically talking about 6U and 3U VPX. Why VPX? Because it allows you to use the very same fabrics, as Aaron mentioned, PCIe, for example, on 3U, and in 6U, typically 10 gig or InfiniBand for very fast data movement through your multiprocessor system. So, and this allows you to do something which is called knowledge-assisted processing. I won't go very deep on this, but basically it allows you to load mission data prior to your mission in a data store, which is on board, and it allows you to know where you are and extract data from your data store and compare it to what the sensor is seeing in near real time, so that you can actually be a lot more intelligent about acting on the real-time data that you're receiving off your system. So this is a simple diagram just explaining what I've been talking about up until now. The idea that stuff that's developed in the desktop or indeed in a data center can now be deployed in medium to small form factor systems based on the Intel architecture or Intel plus GPU architecture, for example, to really greatly accelerate your application in the field. And the reason for doing that is it greatly enhances operational effectiveness of these platforms. It also means that the back-end processing node, which is typically a Linux cluster, can be multi-purpose. It can have a multi-mission capability. It might not just do radar. It might have multiple sensors on it, or it might be able to be adapted for use in different scenarios, operational scenarios. That's where the real payoff comes by using these open architecture systems. So in addition to that, GE offers a software environment that we call Axis. And what it's aimed at is providing an easy-to-use graphical user interface along with a very high-performance inter-process communication middleware library. And we've introduced recently an open API, which is called MPI, into this offering, which means that customers can use this in the knowledge that there's no vendor lock-in. They can decide to change vendors. And indeed, that's one of the key aspects that our DoD customers want, is they want to be able to compete multiple vendors against each other and buy these boxes from different vendors at different points in time. So what it means is you really have to be able to put together a compelling value proposition to stay on these platforms over time. The other point I wanted to make on this slide is that by having a hardware abstraction layer along with these open APIs, it allows you to move your application, as Aaron mentioned earlier, vSpL API for libraries for DSP and math, and also the MPI for the middleware inter-process communication. It means that you're not tied to the particular hardware generation that you're at. You can take advantage of Intel's microarchitecture updates as they come to market to get the next performance boost. Just a quick screenshot here showing the environment that our GUI offers. And the real key here about this, and I won't go into each screen, is that it allows you to see your application mapped to your embedded system in a way that allows you to optimize it for size, weight, and power. In an HPC cluster in a data center, people do worry about heat and power and performance, but within a deployed system, it's much more critical, because more weight on an aircraft, for example, equals less loiter time and less operational effectiveness and less range out in the field. So with the Access middleware, the MPI implementation, again, we're offering the ability for people to develop on desktop machines and move that application straight into a lightweight, portable, deployable system. And typically the interconnects range, as Aaron mentioned earlier, so we support PCIe, we support Ethernet, InfiniBand, and legacy interconnects for power architecture as well. And here's where the rubber meets the road. I mean, you can take such an environment and actually start developing your application before you get the embedded hardware, which means that customers can really shorten their time to market. And our environment supports people even before they get the rugged hardware, and way before they even get the lab system. We're able to engage and show customers what that performance is going to look like. And this is where an example of technology insertion. So our first generation 6U platform with two Sandy Bridge generation Core i7s would give you about 2 gigaflops per watt. And within the same power envelope now, with our latest 4th gen platform, we can deliver a lot more processing power within the same power and cost envelope. And that's what customers want. They want to be able to upgrade over time. So just a quick slide here to show an example of a 3U multi-board system using PCIe interconnect, using sockets to move the data across our latest generation, 4th generation Haswell 3U boards. This is running an image processing application for a ground vehicle ISR application. And the next slide shows a multi-board 6U VPX system, and these are typically aimed at higher performance, maybe radar or image processing applications, which might be airborne as well. And the cooling technologies, the advantage that we have with some of these systems is, both in 3U and 6U, in fact, is that these can be conduction cooled, especially if you take on board what Brian mentioned in his first presentation about how to get the heat out of the sidewall. These are not products that require exotic cooling techniques, but they would benefit from the type of cooling techniques that Brian mentioned in his presentation. So in summary, I hope I've just taken a quick moment to illustrate some of the advantages of using a Linux-based open architecture platform for an embedded application for back-end processing. And again, the link to knowledge-assisted processing techniques and analytics and data that might have been gathered in previous missions or from previous platforms, say satellites or other assets that might be able to enhance the operational effectiveness of the deployed platform in the field. That's where this really pays off. It allows people to integrate the real-time signal processing together with very advanced data processing and analytics out in the field. And that's all brought together by not only the software that we can offer, but the VPX form factors that are out there. So with that, I'll thank you very much and hand back to John and over to the next presenter.
Thank you very much, Michael. And this brings us up to our last speaker for the day. And once he's done, we will start our Q&A session, so please get your questions in there. And now to present our final speaker is Greg Powers of TE Connectivity. Greg?
Great, thanks, John. I'm Greg Powers, Business Development Manager for TE Connectivity's Aerospace, Defense, and Marine Division. I'd like to briefly discuss connectivity considerations when managing SWaP and ISR systems and how things like functional density are leveraged. So ISR systems typically generate and manage massive amounts of data. They're renowned for the needle and haystack scenario. They're typically very high performance, and to manage SWaP, they strive for the highest practical functional density. This is a key point in connectivity considerations, and by maximizing the functional density, the designer can maintain high performance while minimizing SWaP. ISR systems are also becoming more and more embedded computing oriented in order to accomplish local processing. Modular, scalable solutions are very beneficial in this regard as they reduce time and cost, they improve availability and reuse, and allow multiple compatible devices and vendors to be involved in the system configuration. A primary trade when considering connectivity in ISR applications is performance versus cost. This is the C in the acronym SWaP-C. We'll focus on SWaP and functional density in the coming slides, but a prudent approach to connectivity can significantly influence system cost. Selecting components with signal integrity and mechanical integrity headroom will assure system performance. They can extend the life cycle of the system and potentially allow for upgrades without significant redesign. Selecting components that are modular and scalable and that support standard packaging practices encourage reuse and help to control the C part of the equation by maximizing economy of scale and minimizing the designer's learning curve, the qualification costs, and things like that. Let's look at some connectivity examples at the leading edge of ISR technology today. The primary theme of this slide is increasing functional density. This means as interconnect densities plateau, the data rates or throughput is increased to support the growing data demands. All of these board-level data solutions are either matched impedance copper or fiber optic based. They're also modular and scalable for packaging flexibility ranging from small form factor to 6U or larger. The multi-gig RT2 and 2R are the lightest VPX connectors and have been demonstrated at data rates exceeding 10 gigabits per second. They're dual use, meaning space compatible for all the upcoming VITA-78 space VPX ISR applications, with the original RT2 being recommended for VITA-47 environments and the newer RT2R being recommended for VITA-72 environments. The VITA-66 and 67 modules are fiber optic and RF respectively and provide very high density backplane disconnectability, with the VITA-66 modules featuring the MT termini and the RF modules the high performance SMPM termini. The VITA-62 multi-beam XLE complements the VPX data connectors as a dedicated high-capacity power supply interconnect. Moving on to the Meslock family, the Meslock family increases the functional density for XMC applications with improved signal integrity and is referred to as the VITA-61 XMC 2.0. It also features significantly improved mechanical integrity over the original VITA-42 components and features the Minibox 4-point of contact separable interface and highly demonstrated BGA board attach. Finally, the Fortis ED family was specifically designed as a next-gen dual-use mil-aero connector. Again, it features the Minibox contacts. It's modular, comes in multiple configurations, and features data rates exceeding 12 gigabits per second. The Fortis has multiple shell and shield options as exemplified in the Fortis LRM connector shown on the bottom right. The connector provides a high-performance alternative for non-VPX applications. It is not VPX compliant, but it is VPX compatible in that it supports many of the same packaging practices. And let's take a closer look at two of these products, the VITA-46 compliant multi-gig RT2R and the soon-to-be-released VITA-66.4 fiber optic module. So as we move along, this slide provides a better understanding of the VITA-46 compliant multi-gig RT2R. It's really a showcase of lessons learned in the mil-aero industry over the past 40 years. It couples the right materials for applications ranging from fighter jet-based ESA radar to ISR payloads. And it has 4 points of contact at the separable interface for optimal level of redundancy. It has advanced manufacturing features like compliant pin board attach, which is capable of penetrating conformal coat, and is installed via flat rock tooling. And it also features a new level of signal integrity that has really transformed the next generation ISR platforms from megabit per second to gigabit per second. When coupled with the available machine guide hardware, it's VITA-72 rugged and ready for the most demanding ISR applications. So I think that's a good glimpse at the anatomy of the VPX connector. Moving on, let's take a look at the soon-to-be-released VITA-66.4 fiber optic module. Fiber optics are becoming more and more practical and deployed today, and the VITA committee has been working very diligently to enable solutions. Although able to support any VPX embedded computing application, its real strength is unleashing the power of 3U small form factor constructions. It's similar in concept to 67.1, VITA 67.1 I should say, which is the RF module shown on the lower left. And both can actually sit side by side in a standard 16 wafer module footprint. It features, the 66.4 I should say, features the 1MT ferrule and is presently capable of carrying up to 24 fiber optic lines within VPX guidelines. The VITA 66.4 draft standard it's in the later stages of development and should be released in the upcoming year. Let's move on to some input-output topics and what's going on there relative to managing SWaP via functional density. So as this slide indicates, to enable more data flow, the industry is installing fatter pipelines. In the lower left, you see some legacy solutions that were targeted at lower data rates. For instance, the Quadrex contacts were originally designed to support 100 megabit per second Ethernet. In contrast, in the upper right, you'll see a variety of fiber optic interconnect, with the MC6MT-based connector being an extreme example of functional density. That can hold actually multiple MTs in a 38999 style shell. So a primary area of interest is the fast copper connectors shown in the center. These products are providing robust solutions to those seeking elevated data rates, but possibly not ready to make the leap to fiber optic technology for one reason or another. We'll do a quick examination of the C-Lock FastX. So as we take a look at this FastX connector, it comes in two configurations, a single insert size 11 shell or a 4 insert size 25 shell. It has integral wire management. It's easy to assemble and field repairable. It's been engineered for very low crosstalk and features a continuous shield through the connector. The 100 ohm insert has 8 standard 39029 size 22 contacts per insert. And the 100 ohm characteristic impedance makes it suitable for Ethernet and a variety of other 100 ohm protocols. So moving on, we'll take a look at the internals of the connector. This slide depicts some of the physical features behind the impedance control, specifically the differential pair and shield management. It also shows the modularity and scalability of the interface, which can be populated with the 8-position 100 ohm insert or a variety of other inserts offering a selection of power and density. So this interface is very flexible and fully capable of supporting things like 40 gigabit Ethernet in a very flight-worthy package today. Finally, let's touch on some of the fiber optic solutions for use in ISR systems. And moving on to this next slide, we'll see that the Deutsch brand MC5 multi-way connector uses the tried and true 1¼ millimeter ceramic termini and is deployed in many systems today. It was carefully engineered for precision performance in the most adverse ISR applications. As you can see from the images, the family is also designed for ease of maintenance with a removable socket holder to allow access to the termini end faces for cleaning and inspection. The connector is suitable for both multimode and single-mode fiber and is rated at more than 1,500 matings. And another example of a high-performance and well-demonstrated interface is the 83526 expanded beam. This was originally developed for ground tactical applications, and the interface can also be found in applications ranging from military airborne EW systems to commercial aircraft in-flight entertainment. The expanded beam technology is very resistant to contamination. It's a non-contacting interface with some of the highest durability on the market, and also it's the easiest to inspect and clean. TU works with a variety of standards organizations to provide better and more fat pipe solutions. One of these is exemplified by the present work being done within the SAE to optimize performance of the standard 38999 with the 29504 contacts. So as you can see, TE is working to assist in the management of SWaP and ISR systems with a drive to increase functional density at all packaging levels. As we say, every connection counts. Thanks, and that's it for my portion of the presentation. Back to John.
Thank you, Greg, and thanks to all the speakers. Excellent presentations. How about we get right to our Q&A session? First question from the audience is for Aaron Frank. Is PCI Express the only option for multi-core today?
Thank you, John. Excellent question. I'm happy to expand on that. In the same way that we've seen the collapsing of multiple separate processing chips into a multi-core processor, we're also seeing the convergence of processing and connectivity. The one common element is PCI Express on almost every processor, every GPU, and every FPGA and DSP engine out there. We're also seeing those converging with networking elements. So 1 gigabit networking cores are being brought into the processors, 10 gig, 40 gig. So PCI Express is not the only fabric. However, I think as Greg mentioned about the design balance between performance and cost, I'd like to add that the cost is not always a dollar cost. It's also the cost of power, cost of integration, and the ease of development. And the key here is to right size for an application. So as we look at bringing a SWaP system down in smaller in size into something like a 3U board, once you put a processor and memory on a 3U board, you don't have a lot of extra space to add the extra complexity of extra circuits for something that's not native to the processor. We know that PCI Express is generally used even to connect external fabric chips. And by using PCI Express, you really get the best possible transfer rates native to the processors in the smallest possible SWaP space. Tie into that software, middleware to allow you to use PCI Express for things like OFED or shared memory drivers, and you have the best of both worlds: the ability to use the highest bandwidth fabric as well as ease of development. So it's really about right sizing into a small SWaP space.
Thank you, Aaron. Our next question is for Greg Powers. It looks like 10 gigabits per second is about it for the RT2 or RT2R. Is that a correct assumption?
Well, I think that is becoming more the mainstream. The VPX specification was originally designed for 6.25, but it's gone beyond that. People are looking at 10 pretty regularly now. We've had folks demonstrate above that, upwards of 14. But the connector is one component of the entire channel. So it really depends on a lot of the context of the system as well. The board design, the board materials, especially the distance that the signal is intended to go. And that brings the entire technology of fiber optics more to light, no pun intended. But and the VITA committee has done a very good job of provisioning for that technology to be invoked, very seamlessly. So I think that pretty much covers it. We're pushing the envelope, and we're going to continue to do that.
Thanks, Greg. Next question is for Brian. How often do you recommend thermal grease or phase change material used to reduce junction thermal resistance?
Yes, thank you. That is a good question and something that we deal with a lot. And basically, there's a lot of considerations to take when you're either speccing out a thermal grease, a PCM, or even a gap pad as your interface material. And a lot of that has to do with what type of heat flux you have, what type of operating conditions, whether it's steady state or there's transient operating conditions. So there's not one great recommendation. It's kind of a case-by-case basis. But if the person asking that question had more input as to what kind of system they're looking at, we would be happy to dive in and give you a much more thorough answer on what type of thermal resistant or thermal interface material might be applicable for their system. We have done stuff where we're implementing phase change material at the actual junction level to reduce the duty cycle of certain electronics, and there you can see pretty good degrees of thermal resistance lowering by averaging that heat load out instead of sizing for the full heat load. And there we can do a lot to help, but it's really a matter of their heat flux that they have and what their operating conditions are.
Thank you, Brian. I've got a question here from Michael Stern. Does GE's Access software only support Intel architecture platforms?
Thanks, John, and thanks for asking that question. The beauty of the Access software is that it abstracts away from the hardware, and with the open middlewares that we use, including the libraries for math and DSP, and also the open MPI middleware, we can actually run across Linux, Windows, and VxWorks platforms, and indeed across different architectures in the same box. So, for example, we have some 3U systems that are using peer-to-peer PCIe across a 3U VPX platform, and we might have a PowerPC in slot 1 for doing some real-time control type applications, and then have an Intel plus NVIDIA GPU in the same box running Linux. And we're able to move that data from the VxWorks platform across PCIe over to the GPU platform for number crunching, and then with VxWorks in slot 1, you've got real-time control for the platform. So the answer is no, it's not tied to just one fabric or one platform. It's portable from generation to generation and across different interconnects, including Ethernet, InfiniBand, PCIe, SWaP I/O, and for people who've been around for a while, Star Fabric.
Thank you. Yeah, Star Fabric goes way back, doesn't it?
Yeah.
Next question. This one's not assigned, so I'll throw it out there, whoever wants to take it. What, if anything, is each of you doing, well, I guess it's for everybody, is each of you doing in the area of RF convergence for DoD ISR applications? Try and be as specific as to what effective solutions you are examining. Who would like to go first?
So I don't mind taking that one first. My focus has been on back-end processing. On the RF side, today we don't have a particular offering, but what we do have is the ability to interface to standard interconnects. Like a lot of our customers are using either, as Aaron mentioned, PCIe coming off an FPGA front end, which is doing down conversion from the RF side, or in some cases, lots of 10 gig links, like from a radar front end. So our focus is on providing the open architecture back end.
Okay. Thank you. Who would like to go next? Aaron, you want to give that a stab?
I'm not sure that I can speak intelligently on that one, so I'm going to have to pass on this one.
Okay. Brian or Greg?
This is Greg. I'll take a stab at it, but I think we're, at the physical layer, we're a little bit more obvious than the other folks on the phone here. And certainly we're working to provide the digital and the RF and other media, including optics. So there, things like isolation and whatnot are taken care of quite very much. But that's it for the physical layer, I would say.
Brian, you want to try, or are you good?
Sure. On the RF convergence side, we don't get into a lot on the actual RF convergence, but basically we treat anything like a heat source, and we can run thermal management on the backside, and we've done a plethora of different technologies and solutions there. So again, it kind of is dependent on their boundary conditions and the actual heat loads, but we can advise there if there's more detail available.
Okay. Thank you. Next question for Aaron. You mentioned the AltaVic vector engine and then an Intel AVX vector engine. How do they compare?
Well, both of those engines are single instruction, multiple data processing engines, and they're highly similar in terms of what they can do in terms of functionality. Probably the biggest difference is that the AltaVec engine is a 128-bit wide engine, which allows you to operate on 4 single-precision 32-bit words with each cycle, whereas in the Intel, the AVX2 engine is a 256-bit wide engine, which means you can have 8 32-bit single-precision words operating in parallel. That being said, both Freescale and Intel are looking at next generation, going up to 256, 512, and even beyond for higher level of vector processing. So I expect that it'll simply be both AltaVec and AVX that continues to grow over time.
Thank you. Next question for Brian. How does flattening a heat pipe affect its heat transport capability?
Yeah, thank you. That's a good question. Flattening a heat pipe will affect the total amount of power a heat pipe can move. Basically, how you account for that is instead of determining the power capability with the actual physical diameter, you use the hydraulic diameter of the flattened cross-section, and then you would run a similar power curve, which is basically trying to figure out how much the wick structure can create a pressure drop that overcomes the various other pressure drops within the heat pipe, so the vapor pressure drop, the liquid pressure drop, and the biggest one is the gravitational head pressure drop. So as long as you have the wick structure correctly sized to overcome the pressure drops in your system, you can move the full heat load. But by flattening the heat pipe, you are cutting down the vapor space slightly, so you will have to take that into consideration when you're running your calculations.
Thank you. Question for Michael Stern. What system cooling techniques are typical for deployed HPEC platforms?
Thanks, John. So, as I kind of alluded to in my presentation, there are some very exotic techniques out there that are required for higher power per slot count. So, in the products that we're bringing to market, we try to make it so that our products are conduction coolable. Aaron mentioned 3U being very good because you got two card edges next to a fairly small form factor and heat source. In 6U, what we are able to achieve by staying within about, under about 150 watts per slot is offering a conduction coolable solution with meaningful performance in that grade. Having said that, we do offer airflow through Vita 48.5 form factors for some customers who want to get the most out of their application. But what we're hearing from the market is that a lot of our customers doing deployed systems cannot employ special cooling techniques. There are people out there who will because they have extremely high performance requirements, but a lot of the ISR applications do not have the thermal interfacing capabilities to use very special cooling techniques. At least that's my experience. So conduction cooling is a good way to go.
Thanks, Michael. Next question is for Aaron. Aaron, do you have any challenges with meeting security architecture requirements using Intel processors because of the necessary use of the Intel PCH?
Not necessarily because of the PCH. Intel does have a security platform called the Intel Trusted Platform technology for secure computing. It is very similar to, in Power Architecture, they have a secure boot. In ARM, they have a highly assured boot mechanism. In all cases, it's a mechanism where there's extra circuitry added on board that can hold encryption keys, can validate signed BIOSes and kernels and boots and software that's running. So in a trusted environment, those techniques, including the Intel Trusted Platform, can be used. There's also techniques such as multiple root PCI domains that can be used for multi-enclave systems for secure enclave separation, and built-in encryption and key management with storage technologies that are pretty common in today's computing technologies. So we haven't hit any security requirements that we can't meet yet.
Thanks, Aaron. Next question for Greg Powers. You mentioned optimizing functional density as a way of managing SWaP. Why is this necessary?
Well, it really comes down to the fact that, material science has not changed dramatically, and there are basic things like dielectric withstanding voltage and things like that prevent the densities from getting much higher in terms of, connecting to the board. There's the board layout itself that is a challenge. So as a way, in reality, the density of the connectors themselves is somewhat plateauing. To offset that, what we focused upon is the signal integrity and the impedance matching, and therefore the functionality is increased while the density is plateauing. And so the functional density is truly increasing, but this really shines a light on the need for superior signal integrity, and that's one of the areas that we're really focusing on to continue to drive the systems.
Okay, time for a couple more questions here. Michael, what data and expansion plane fabrics are used for deployed HPEC platforms?
Thanks, John. So I hope I made clear in the presentation that what we're trying to do is map high-performance computing architecture straight across to embedded 3U and 6U VPX platforms. So in the 3U world, we're typically using Ethernet for control plane and PCIe for data plane. on a peer-to-peer basis. The advantage of moving to 6U is that you get much more scalability, and the software and architecture is made for that. So you think about an HPC system in scientific computing, for example, at some of the DoD labs or at high energy physics, you're talking about thousands of Xeon multi-core processors and thousands of GPUs with many cores, all linked together typically by InfiniBand or Ethernet for data plane and Ethernet for control plane. Those very same architectures are what we're talking about deploying here, both on 3U with PCIe and on 6U with our InfiniBand and Ethernet data plane.
All right,
and the software that goes with it.
Oh, sorry, Michael. Time for two more quick questions. Is the Fortis ZD connector VPX compliant, Greg?
No, it's actually not VPX compliant, but we would call it compatible in that it can be it can actually sit on the same card edge. It can be packaged in very much the same way as the VPX ecosystem, and it's made specifically for mil-aero applications. So it's really meant as a non-standard connector to open up designers' creativity.
Okay. I think Michael had a follow-up on Secure Boot. Do you want to kind of throw that in, Michael?
Yeah, thanks. So Aaron mentioned about the PowerPC architecture and the Intel architecture having capability for trusted execution, and that, of course, comes with the chipsets, and we support that as well. However, in addition to that, on some of our products, our latest 4th-gen Haswell products, we also have an anti-tamper capability on the board, which is an additional off-the-shelf starting place for customers to implement their own custom power bring-up capability and also anti-tamper detection capability. It's an emerging area where, especially for foreign military sales, U.S. DoD integrators are looking to make sure that the platforms that they deliver only do what they say on the label and can't be used for other purposes.
All right. Thank you, Michael. Thanks, everyone. That brings us right up to our time limit for today. I'd like to thank Brian Musica, Aaron Frank, Michael Stern, and Greg Powers for speaking today. And Advanced Cooling Technologies, Curtiss-Wright Defense Solutions, GE Intelligent Platforms, and TE Connectivity for sponsoring the event. This ECAST will be archived online today and will be available for 1 year. There will also be an MP3 version of the event available. Thank you all for attending, and I look forward to seeing you on future Open Systems Media ECAST. Goodbye.